So the very last thing we can do is just solve these equations that we've come up with and actually see how the universe evolves with cosmic time. And the first thing we want to do is look at the evolution of the energy density. And we can note we can do this for three different cases. P equals WE, where W equals a third for radiation, W equals 0 for matter, and W equals -1 for lambda. So, fluid equation, writing P equals WE, just becomes E dot plus 3E A dot over A, 1 plus W equals 0. And we just integrate that. So the integral of dE over E is equal to -3, 1 plus W, the integral of dA over A. Which obviously gives us a logarithmic solution, but we can then take that out. So that you get E of T is just equal to E0 A of T to the -3, 1 plus W. And so just looking at what that means for those three different equations of state, we get that for matter, E of T is proportional to 1 over A of T cubed. That's not surprising, that's exactly what you would guess. In other words, if I double the size of a sphere, its volume goes up by r cubed by a factor of 8, and so the density goes down by the same factor. So for matter, that's exactly what you expect. For radiation, we just have E of T is proportional to 1 over A of T to the 4. And you can think of this as being a number density effect, which is just 1 over A cubed, times a redshift effect, i.e. the energy of a photon is E equals hc over lambda, and lambda is proportional to A. So you have a number density of photons that goes down by 1 over A cubed, but the energy of your individual photon is also going down by 1 over A, so the overall, it's 1 over A to the 4. And then you have the very weird one, where you have for lambda, E of T is just equal to a constant. And remember, E is an energy density. It's not an energy, so it's joules per cubic meter, or something like that. And so what that means is that as the universe gets bigger, the contribution from the cosmological constant gets bigger as well, because you multiply it by the number of cubic meters in the universe, and it's more and more and more. And so from this you can see that there are in fact going to be distinct periods in the history of the universe. Currently we're sort of at the point where the cosmological constant is just taking over. But as we run the clock back, and the Big Bang's down here somewhere, you're going to go through periods of matter dominance, and eventually radiation dominance. And so the universe at the moment is in an unusual period where it's actually kind of got not so different contributions from matter and from the cosmological constant. But you can roll it back and just look, because you can scale things according to their relative densities, remembering that the total density at any given epoch, not, right now is not in physical joules per meter cubed again, but the critical density at any given epoch is always going to be the critical density. So you can work out those changes, and so you end up with a change of scale factor from matter to lambda when the universe was about 3/4 of its current size or something like that, whereas the change from matter to radiation was way back when the universe was 1,000th or less of its current size. So we also do need to worry about what these are going to do in terms of the scale factor with cosmic time. So having looked at the behaviour of the density, we can then look at the behaviour of the scale factor. And the scale factor is going to be solved in a slightly different way. That's going to be solved from the Friedmann equation. A dot over A squared equals 8 pi G over 3C squared minus KC squared over A squared. K equals 0 for simplicity. You can solve it for more than one component. And so A dot over A all squared equals 8 pi G over 3C squared E naught A to the minus 3 1 plus W, just substituting in here from the fluid equation. And for W not equal to minus 1, this becomes dA by dt is equal to the square root of 8 pi G over 3C squared E naught A to the minus 1 plus 3W over 2. Separate, integrate. And that just gives you A of t equals t over t0 to the 2 over 3 1 plus W. And then for W equals minus 1, we get H equals A dot over A equals 8 pi G over 3C squared E to the half equals a constant. So this is the integral of dA by dt, so dA over A i.e. the integral of dA over A is equal to 8 pi GE over 3C squared, the integral to the half, the integral of dt. And that means you can substitute in. So for radiation dominance, you have A is proportional to T to the half. For matter dominance, you have A is proportional to T to the 2/3. And for lambda dominance, you have A is proportional to E to the HT. So what you can actually do, therefore, is go through and work out in some degree of detail what the evolution of the universe is actually going to be like over cosmic time. And so I have three different possibilities here. So for a flat universe, dominated by each of the different things, if I plot T versus A of T, then radiation, should use some different colours, radiation will do something like that. Matter will do something similar, but a little bit less steeply. And then lambda is just an exponential growth. And of course, it's actually steeper than these in terms of what it looks like. And so that's your sort of general sketch of what the scale factor of the universe is going to look like in each of those cases. And then you can also think about what the real universe is going to look like. So these are model universes, if you like. The real universe that we want to worry about consists of all of those different things. And so you can actually plot that in a little bit more detail. And so if I do that, then I have a period of radiation dominance, followed by a period of matter dominance. And of course, I should have been using my different colours for this. So you have a period of radiation dominance, followed by a period of matter dominance. I'm sorry, this is very badly drawn. Followed by an exponential expansion. So rad, matter, lambda. And that means also that we know that the future of our universe now, you know, barring some very unforeseen things, is that it will expand forever at an ever increasing rate. All of the galaxies will get further and further apart. And eventually you will end up with individual galaxy clusters which are gravitationally bound and everything else, you know, way out of sight. So we're not going to have a fate of the universe which slows to a stop, nor one which falls back on itself. And so that's quite remarkable. And so for people who are interested in knowing a little bit more about cosmology, I will put the Newtonian cosmology notes on this website as well under this week. You don't need to look at these. These are just in case you're interested in knowing more about it, because obviously I've just scratched the surface here and shown you that. And if you look at Newtonian cosmology, you might also see in a few places the difference between the two. And so that wraps up cosmology. It also wraps up this course. Thank you for listening. I realise that this has been a singularly different experience for you, for me, for everybody. I don't know what's worked well and what hasn't at the moment, so please tell me that in your feedback. And good luck in your exam.